Okay, so we're resuming now with Physics 1C, the last hour for October 1st. And we're solving this problem. We gave the students some time to write down their own equations so we can compare them. All right, we got two junction rules we got to write down. Let's do them. We'll call this junction 1 and junction 2 or something like that. So the first junction, we've got I1 and I2 coming in and then I5 going out. So we're going to write I1. Here, let me make this black. So it's I1 coming in, I2 coming in. Those are both positive. And then minus I5 because it's going out. For the second junction rule, for junction 2, we're going to get, let's see, junction 2 has I5 coming in, so it's positive. I3 coming in, so it's also positive. Oops, keep doing that. I3, and then I4 also going in, so all three are positive here. All you think is Intel. Okay. All right, so for the loops, we've got three equations for those as well. So for loop 1, we've got, let's start from here. So we go in the same direction as I1, so I'm going to have negative 200 I1. Oh, I3, I5 processors, okay. All right, negative 200 I1, we go around here. This is the loop we're doing, so we're going against the 40, so it's going to give us negative 40 volts. And then we're going against the current here, so we get a positive sign. So positive 80 I2. That's equal to 0. Let's do loop 2 right here. So for loop 2, this one right here, let's start in this corner right here. So going up in this direction, we'll have negative 80 I2. It's 40, not 400. Yeah, there's a decimal there. I don't know if you guys saw that. Negative 80 I2. We're going in this direction. We're going to get a positive 40 then. And keep going this way. Positive 360. And then going this way again, we get a plus because we're going against the I3, 20 I3. And then let's leave some room there, and we'll say loop 3. Coming around here, let's start here for loop 3. Going up this way, we're going to get a negative 20 I3. And then negative 360, because we're going from positive to negative. Keep going, negative 80. And then positive 70 I4. I saw someone just write down the answers. Let's see if we get the same thing. Negative 40, positive 80, 200. Yep, you agree with this one. And then 360 and 40 are both positive. Negative 80 I2, positive 20 I3. Yep. And then you wrote negative 80, that's there. And then positive 70 I4. Negative 20 I3, and negative 360 volts. Great. So hopefully everybody was able to get these same equations. If you weren't, that's okay. It's definitely easy to make mistakes here. Hopefully all you did was you got a negative sign wrong or you wrote a number wrong here or there because, you know. So we want to solve these. One thing you might notice is that these two equations to the left are the only ones that contain I5. So we can immediately eliminate I5 from our consideration by just adding together these two equations right here. So we'll do that, and we'll get a fourth equation that we can use. So this is going to give us basically that I1 plus I2, and then well plus I3 and I4 as well. Is going to give us, those are going to add to 0, and those are the equations that we want to use. We are going to rearrange them to be used with our reduced row echelon method. So this one's going to become negative 200 I1. Plus 80 I2 plus 0 I3 plus 0 I4 equal to 0. This one's going to become 0 I1 minus 80 I2 I made a mistake here. This should have been equal to, sorry. Loop 1, we had the negative 40 as well, so that becomes positive 40 over here. Okay, this one, there's 0 I1s, negative 80 I2, positive 20 I3, and then 0 I4 should be equal to 360 plus 80. 36 plus 8 is going to be 440, I believe. No, 360 minus 80. No, what am I doing? These are the numbers that I'm adding together. 40 plus 360, that's 400, and it's negative 400 volts. And then finally, this one here, there's no I1, there's no I2, negative 20 I3, plus 70 I4 is equal to 36 plus 8, 440. Yeah. Okay, does that all look good to everybody? Did I make any mistakes that immediately jump out? So let us construct a matrix with these. Do it right here. This is going to be a 5 by 4 or something like that. First equation, 1, 1, 1, 1, 0. Second equation, negative 200, 80, 0, 0, positive 40. Third equation, 0, negative 80, 20 and 0, negative 400. Final equation starts with 2 zeros, then you get a negative 20, you get a positive 70, and we get a 440. And that will reduce your echelon form down into, we need to go, what, rows is 4, columns is 5, create the matrix. Now 1, 1, 1, 1, 0, not 9. Negative 200, 80, 0, 0, 40. God, I really wish I had a numpad on this keyboard to make this way faster. Negative 80, 20, 0, negative 400. And then 0, 0, negative 20, 70, 440. Yeah. If you're testing in person, I mean, I would actually I would quite literally hand out calculators so that people can use them during class if they didn't have them. So, I don't know if I said that or not. I said it now. So I1, I2, I3, and I4, I believe it was something like 1, 3, 6, 8, and I think this one was negative. Although I wasn't paying close attention. Let's see what we got. 1, 3, negative 8 actually, and then positive 4. So this is negative 8, this is positive 4. Negative 8, positive 4. Equals, 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 amp, 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 amp. Here we go. So if you solve by hand and you don't get the right answer, that means you made a mistake. Right? If you solve by hand and you don't get the right answer, that means you made a mistake. So try to solve it by hand again. You can use the same method in this case as we did in the first one, where you can solve each one of them for... Well, can you? I don't know. Let's see. These two have I2 in it, and this one has I3 and I4. So you basically solve this one for I1, probably solve this one for I3, probably solve this one for I3, and then plug that into here, so you get I4 in terms of I2, and you plug everything back into here. That'd be the way to go, in my opinion. We could do it on the stream here, but I don't think you guys want to watch me do a bunch of algebra again. Something tells me, which is why it's really nice that we can solve these simply by using this method here. Okay. Any questions? That's the last one of those we'll do.
pretty thoroughly covered these type of problems. You'll see quite a few on your homework, and this method is something that's going to be helpful for solving. So the thing about this is that there's something that's physically unrealistic about this, by the way. The fact that there's not a resistor here means that if we were to actually construct a circuit like this, I think you'd have like some kind of infinite current flowing through here or something like this. I mean, you can get an answer because according to this, I1 plus I2 is equal to I5, so it should be equal to 4 amps. But yeah, it's kind of, we kind of put it in here, so apparently it's 4 amps. I don't, it's, yeah. Would there be another column? Well, keep in mind that we eliminated I5. We eliminated it. So we reduced our problem down to only having 4 variables. So, yeah. I'm just saying that like sometimes these problems, I'll just show you. I guess it's the easiest thing to do. Where did the circuit construction kit go? It's right here, right? So if you remove the here, can I just set it to 0? Wait, so why is nothing happening here? What if we just put a wire in here? Do I need to like reset dynamics maybe? Is that what I need to do? Huh, why is it not working anymore? Well, we'll just reset everything. So here's what happens. Suppose that we just take a system where we plug something in that has no resistance. So we'll have one segment here where we put a resistor in here. Okay. And we need to put a switch too. Wire. And then up here, we're gonna drop this right here. So now we've got a resistor and it's 10 ohms, but the resistance of this wire on top is 0. So if we close this, okay, what is going on? How come? Oh. Thank you. I appreciate that. The play button. Okay. Yeah. See the problem? So for like basically what happens now is that like look at the current in the middle section. There's now no current in the middle section, and you get an infinite amount of current out here. And if we were to do something similar to what was happening in the previous problem, what we would need to do is, let's split this junction right here. Split junction. Oh no, we'll leave that one the same. So what we'll do is, here, let's remove this. So what we'll do is, we're going to drop, I wonder what it's going to do with this. I don't really know, actually. So we're going to do that, but then we're going to introduce, here, move everything down. So we're going to put our 4th segment in here. Do we throw some extra batteries in here too? Might as well. So let's drop some more batteries in here too, to make it a little more similar to what we were doing. Hey, let's cut it out with the, okay, but this is a closed loop. That's fine, whatever. We'll do one more. Right here. Right here. Maybe it won't cause us problems as long as, okay, let's close this. Okay, I guess it's okay. I guess that this looks okay for this. I'm just wondering in the real world if you connected something like this, if you'd have a problem. I guess because technically these two would combine to produce a resistor here, so it's okay. So do I need to put in more batteries? Is that what I need to do? I don't know. Let's see. Drop a battery there, go there, go there. Go here. Oh, something's disconnected. Is that disconnected? Huh, now it's not doing anything. I don't know, maybe I've overloaded it or something like that. Okay, let's not read too much into that. But, yeah, so I guess maybe there can be current here in this this portion that we called I5. The polarity switched. Oh, are all the battery, let's see, was that what was going on? positive, negative, right. So we'd have to like make them be a little different here, right? That's what we need to do. Change voltage to something like that. Change voltage. This. And then put this in here. Okay. Yeah, you're right. That was the reason why. Oh, it looks like this one still has nothing running to it. Anyway, okay, so you can scratch what I said. I thought for some reason you'd have an infinite amount of current flowing through here, but I guess you wouldn't. Probably because there is resistance at other places within the circuit or something like that. So we definitely could solve for I5, and it would just be equal to, like I said, I1 plus I2, so it'd be 1 plus 3, so it'd be 4 amps. Okay. Nope. Anywhere you have these branches, like I1 is all the way from there to there. I2 is from here to here. I3 is from there to there. I4 is... So I5 is just between these 2 points right here. Just between these 2 points. The middle segment. Okay, we have about 20 minutes. Yeah, you could add an I6 to the bottom if you want to. And I'm pretty sure it had the exact same value as I5, actually. Because it would also be related to I1 and I2, right? If we draw an I6 down here, it would be equal to I1 plus I2 as well. So the current in this piece and the current in this piece should be the same, I believe, is what you would find if you wrote a current down there. Okay, I want to make sure we actually talk about resistors and capacitors in combination today, so let's do that. And in fact, actually, what I want to do now is to show you this again and give you an idea for what happens when we do put a resistor and a capacitor together. Now, a battery, or a what do you call this? A light bulb is basically the exact same thing as a resistor. So we're going to use a light bulb in this case. And what I want to do here is I want to connect a light bulb in series with a capacitor. And then I want to connect that to a battery. And I want to have a switch as well, so we can turn this on and off. And then, so we want to, for what we do first, I think this is what we want to do. So we've got a battery, we've got a capacitor. We're going to make it 0.2, show value, change resistance, make this as big as possible, and then I'm also going to show value here. Okay, so now what we have is a system that has a capacitor in it, right? And capacitors are open portions of the circuit, effectively. Current cannot technically flow across the capacitor. It's eventually going to charge up, right? And what we're interested in investigating here is basically how long it takes for our capacitor to fully charge. That's what we want to investigate, okay? So if I close this right here, and we watch what happens, the capacitor is going to fill up with charge. And once it finally fills up, it's going to have a polarity that's opposite the battery. The negative side of the battery is on the right, the positive side of the battery is on the left. And once it completely fills up, the current is no longer going to flow. And we can get an idea for how that's happening for figuring out exactly when the voltage here gets to 9 volts. See how it's just ticking up, the voltage? Slowly approaching the 9 volts that's right here. And it's negative just because of the way that I put it. If I put the positive on the positive side, the negative on it, you'll still get this right here. So it's slowly trying to reach 9 volts right now. At 9 volts, would it fire? No, Once it reaches 9 volts, the current's going to stop flowing. In fact, one other thing that I should probably introduce into this is an ammeter. It's going to throw it off for just a second, but if I drop an ammeter in here, there we go. Yeah, the current's already dropped to 0, so it's kind of useless. We would need to use the current chart, I believe, is what we would need to use. There we go. This will show us the current. Should be 0. I should be really close to 0 at least. What do I want to do? I want to get... No, I want to zoom... Yeah, plus. There we go. Here's our current. You can't really see it. It's still really close to 0. Because this is almost maximum. Once it's fully charged, the current's going to stop flowing. You said, is the light bulb lighting up while the capacitor is charging? Technically, this light bulb should be lighting up right now, but there's so little current flowing in the system that's just not happening. Okay. So we can reset this again. It's going to take a really long time to actually reach exactly 9, and we'll see why that is here in a second. But if we reset dynamics, notice that, yeah, the light bulb is lit up as long as the capacitor is charging, but the brightness that the light bulb produces, right? The brightness of the light bulb is related to the power. What's power for a light bulb? We learned it last time. It's I squared times R, right? So as the current gets smaller and smaller and smaller and smaller, the light bulb, it's technically still lit right now. It's just not very bright because there's very little current that's flowing through it. Okay? But yeah, while the capacitor's charging, the light bulb's going to light up. Absolutely. Yeah. Yeah, and I can show you this exact thing in the classroom. It's pretty cool, except really we would just be watching a multimeter do this. Now, what we can do is we can actually play with this setup. I don't know if you got much of a sense for how long this took here, but it's taken a while, right? Now, what we could do now is I'm going to pause the simulation. We're going to reset the dynamics. And what I want to do now is I want to change some values around here. So what do you think is going to happen if I reduce the resistance in this light bulb, let's say by a factor of 50? So what if we go down to 2 ohms? 2.35, whatever. That's fine. And let's leave the capacitance the same at 0.2. That's as big as we can get. By the way, 0.2 farads is huge for... That is a massive capacitor. We don't have anything even remotely close to that in the lab. So let's see what happens now. I've reset the dynamics, so that means that the capacitor plate's no longer charged anymore. I'll even open this, and we'll push play. Now, nothing flows. We have 0 current, but the moment that I throw the switch... Well, look at that. That was a lot faster. Did you see that? It was so fast, we got to do it again, right? So fast. Why would that be the case? Why did it charge up so fast? Maybe 50 times faster. That's right, Nathan. It turns out it's exactly 50 times faster. That's right. So let's pick an intermediary value. Let's go to like 40-ish ohms, okay? I'm just changing the resistance. Ash, pay attention. Don't get distracted. We're gonna reset everything, and it's gonna start again immediately. Here, wait. I like to have the switch. It's kind of unrealistic because you can't really. So we reset everything. Oh no! Can I undo? That sucks. Oh, that's terrible. I'm supposed to reset dynamics. All right. Luckily, this is pretty easy to rebuild this circuit. It's really simple because all we had in the circuit was just a capacitor, right? And then a light bulb, and then some wires. Really, really simple circuit to reconstruct. In fact, we can just connect that one right there. Let me move this here. And then we wanted to change the capacitance. We want to leave it at maximum. And then now we want to change the resistance to about 40 or so. Okay, now let's watch to see how long it takes. A little bit slower, right? Okay, so Nathan's saying lower resistance lets more current flow, and the capacitor gets more charges coming to it. Yeah, that's exactly right. That's it. The rate at which this thing charges up is related to the resistance right here, right? It's also related to something else. It's related to the capacitance. If you have a smaller capacitor, it's going to take a little bit less time to actually charge that capacitor up, right? Yeah, so that's what we want to investigate is how do we show that the rate at which the capacitor charges is proportional to the resistance and the capacitance. That's what we want to show, okay? Because again, if I were to change this one, change the capacitance and make it a really small capacitor by a factor of about 4, okay, and then we reset dynamics, it's also going to speed up the rate at which it charges, okay? Oh, and look at that. You can actually see it really beautifully on this picture. Did you guys notice that? Let me, here. Watch this. Do we need to minus it? To go out to about there. Okay, reset dynamics. Okay, watch this. That's what the current growth looks like. It's a nice curve, right? Do you know what kind of curve it is? Can you tell? What does it look like? Natural log, maybe? Kind of like natural log, maybe about like an exponential. You're on the right track. You're on the right track. Okay. It's in that range. It's like exponential or natural log. We can show it one more time so you can see it here. There's the curve. It's nice. It's gradually approaching, asymptotically approaching 0, right? Asymptotically approaching 0, not square root. Because see, it eventually goes to 0, right? Which means there's an asymptote there. So we need that to show up on our answer. Okay, let's see how quickly we can do this. We got about 10 minutes. We're going to do a derivation, and it's going to involve differential equations. So let's see how we do it.
All right, so we've got a circuit. We've got a resistor that we call R. We've got a capacitor that we call C. And we connect those with a switch to a battery. And we're going to say that the EMF of our battery is E. Okay. And what I'm going to do is we're going to say at time equal to 0, at a time that we artificially call t equal to 0, the switch is going to be closed, which completes the circuit. Okay, so we close the switch right here. We'll use a different color to represent that it's been closed. So we complete the circuit by closing the switch. And now I'm going to say that there's going to be current flowing in our circuit, and that current at any moment in time I'm going to call I. So little I is going to represent the instantaneous current. That current is going to cause this capacitor to become charged, positive on this side and negative on this side. And I'm going to say the charge on the capacitor at a moment in time is Q. So Q is going to represent the instantaneous charge on one plate of the capacitors. And I'm going to say that what we'll do to analyze our circuit right here is that we are going to do a loop rule like this. We're going to do a loop rule. Okay? Starting from this point, we're going to get the EMF, right? You get E. We're going to the resistor. The resistor has current flowing this way, so what do we write down? Positive or negative IR? Positive or negative IR? Current's going this way. We're going in the same direction as the current with our loop, right? Going from there to there. Going downstream, so it's going to be negative. Going downhill. Lower potential. Okay? Same thing, we go across the capacitor right here. We didn't talk about this, but in this case we're going from positive to negative, so we're going to get negative Q divided by C. This because the potential difference across our capacitor is going to be represented, the delta V is going to be equal to Q divided by C. This is just the definition of how that works with capacitors. Okay? And if our loop rule works with capacitors as well, this should be equal to 0. Okay. Next, we're going to try to use this equation to tell us effectively what the current in the system is as a function of time that we saw in that picture just a second ago. We want to find the charge as a function of time as well. So we're going to start off by looking for this one, because we know there's a connection between the charge and the current. What is that connection? You remember? How are the current and the charge related to each other? How is position related to velocity? How is velocity related to acceleration? It's all the same idea. Current is the flow of charge, the rate at which the charge flows, right? The time rate of flow charge, right? So the current is equal to what is it? There's so many people typing. I was sure one of you were going to write an answer. It's the derivative of Q. Thank you very much, Ash. It's dq dt, right? It's the derivative of Q. dq dt, exactly. That's right. So we can put that into this equation, right? So we can rewrite our equation. So it says E minus dq dt. And I believe I'm going to divide everything by R here. Okay. So I basically multiplied through by 1 over R. And then I replaced the I with dq dt right there. We kind of skipped a step. Hopefully everyone can follow that. That's equal to 0. And now what I want to do is I kind of want to rearrange things. I want to get dq dt by itself. So I'm going to add it to the right-hand side. So on the left-hand side, we're going to have epsilon minus q. I want to get a common denominator for these two things right here. So I'm going to multiply this one times c, and then we'll divide by rc. And that should be equal to dq dt. like that. Okay. And then for whatever reason, I'm going to multiply both sides by a negative sign. Okay, doesn't change anything. Just multiplied through by -1. Next thing we're going to do is, this is a differential equation that we can separate the variables. So I'm going to move the CE, Q minus CE to the right-hand side. This equation is now going to become something like this. We're going to have negative dt divided by r times c, and this is going to be equal to q minus c times e divided by... Oh, no, that's not right. Sorry about that. What are you doing? Undo. dq and divide by q minus ce. There we go. Okay. And now we're going to integrate. On the left-hand side, we're going to go from 0 to t prime. T prime being an arbitrary time in the future. On the right-hand side, we're going to go from 0 to q prime, an arbitrary charge at some later time in the future on the capacitor. The left-hand side of our integral, very simple. It's just going to become, negative t prime over rc. The right-hand side of our integral over here, what's that going to give us? It's like a natural log, right? Exactly. So we'll have the natural log of, let's see, q prime minus ce minus the natural log of negative ce. And these are absolute values, right? So don't we drop the negative ce? Isn't that how it works? So what we're left with then on the right-hand side now is going to be the natural log. We can make a ratio now of q prime minus ce divided by ce, and that's equal to negative t over rc. Now we can raise both sides to the e power. We'll get e to the negative t over rc on the left-hand side. On the right-hand side, we're going to just get the ratio, q prime minus ce divided by ce. You multiply the ce to the left-hand side, you get ce e to the negative t over rc is equal to q prime minus ce. We add the ce over here, so we end up getting ce plus ce times e to the negative t over rc is equal to q prime. See, I think something's wrong here. I knew if I did this too fast that... did I drop a negative sign somewhere? From the natural log part here. I think we can't do this thing. Like, I think you actually have to keep the negative sign on this thing. I think what I said was wrong about doing the absolute value stuff. I think that was wrong. I don't know where that came from. I don't know. But I think those absolute values are wrong, because we need this negative sign right here. It needs to show up as negative over here. And then this needs to be a negative sign as well. Mathematically, I don't know. It's the absolute value of the quantity. Huh? Yeah, maybe that has some more meaning when you have numbers involved. Okay. Anyway, what we end up getting then is CE. We can factor that out of here. Times 1 minus e to the negative t over rc. And that's equal to q as a function of time. I kind of, at some point here, dropped the primes, right? We could have gotten rid of the negative sign before the integral. That's what I tried to do by multiplying both sides by a negative here, but maybe ultimately that actually caused a problem. I'll have to think more about it, but we're running rapidly low on time, and I want to kind of get to the point here. So this is our final answer. but I want to notice something right here. In our problem, this was the capacitance C multiplied by E. And what I would argue is that if I take C and I multiply by the EMF of the battery, this is going to give us the maximum charge on our capacitor. That's the maximum value you get for the charge for the capacitor. So a better way to write this would be to write it as Q max multiplied by 1 minus e to the negative t over RC. And now we can kind of see if this makes any sense. So this type of a function right here, what value does it take on at time equal to 0? 1, right? So what's the charge on the capacitor at time equal to 0? Exactly, 1 minus 1 is 0. What value does it take on after we let q go to infinity? E to the negative infinity is 0, so you get q max. So this actually makes sense. At time equal to 0, we have 0 charge on the capacitor, and at time equal to, as time goes on, you eventually get the maximum charge on the capacitor. So the way that we would plot this, if we plot q versus t, would be that it would start off with 0 charge, and it would eventually reach some maximum value that we call q max. Now you'll notice within this equation that this RC shows up right here, right? And it shows up right underneath the time. Well, it turns out that if you look at what R times C represents in terms of the units, it actually, if you take resistance times capacitance, you work out the units, you'll actually get the units of that as time, okay? So what we do is we define this as something called the time constant. They call this the RC time constant. And really what it represents is that after one time constant, you're going to be something at about 63% of your maximum charge, I believe. This would be at 1 tau. And at this location, I believe that you're at about, I think it's about 60% of Qmax. How much are you exactly? Well, at one time constant, this fraction here would be 1 minus e to the negative 1. Okay? When t is equal to RC, it's negative RC over RC, so you get that. And 1 minus e to the negative 1, I believe, is something like 0.639 or something like that. Let's see. 1 minus... Yeah, 0.632, sorry. 63. So technically, I should have said over here that it's about 63% of Qmax after one time constant. So it's a pretty good way of getting a feeling for how long it takes for your circuit to charge up. And that's why when we were looking at the diagram here, that when we reduce the resistance down to a really small value, right, it charges up super fast, right? And because it's R times C, if we make the capacitance bigger, it's going to charge up a little slower. Oh, no, faster, sorry. Because you multiply them. Right? R times C, my bad. Yeah. Okay. So this thing gives you a rough estimation of the time that it takes to tick off. This also tells you something about what resistors and capacitors can really do for you, and this is what we'll finish with today, is just to say that by putting a resistor and a capacitor together, you all of a sudden have introduced a timing element to a circuit, right? Suppose that you design a circuit so that when the capacitor is fully charged, something happens, okay? A simple example of this would be windshield wipers. This is the example we always use. It's like in the windshield wiper element of your car, there's different settings, right? And when you're alternating between those settings, what are you doing? You're quite literally changing. It's usually resistance, I believe, that you're changing by rotating that little knob that changes how fast your wipers go back and forth, right? And by increasing the value of the resistance, you make it take a longer time for the windshield wipers to go, okay? And that makes it a slower switch. Don't clocks use quartz? Do they use a resistor-capacitor combo? So quartz clocks operate off the idea that when you provide electricity to a quartz crystal, it will ring at a certain rate. I don't know for sure whether they use resistors or capacitors, but because it's an electronic device, chances are there's probably some of that in there. Do they use those resistor-capacitor combos to produce time? I don't believe so. I believe that the timing element in a quartz clock is provided by the rate at which the crystal will ring whenever you apply a circuit to it. When you apply current to it.
Okay, so a little bit different, but along the right idea, because it is about like introducing timing into your circuit by having this combination. Do y'all have any questions? That's a really good question, Mr. Miars. Your question is this why they can only accurately predict the charging time for a car from 0 to about 65%, but they can't predict the charge rate from 65 to 80 or from 65 to 100? Huh. That's super interesting. I don't know if it's I think that's probably more about the way batteries work and about how batteries charge, but I don't know. It's a really good question. Maybe you could go read about why they can't predict the charge rate. Because, I mean, in this case, it is predictable, you know. You could predict how long it takes, for example, to get to 80% charge, 99% charge. It'll reach 99% charge in about, probably like 5 time constants, I think. So if the time constant was 10 seconds, it would probably take 50 seconds. Technically, yeah, it won't ever, quote, reach Qmax, but in reality, it's actually going to get there. You know, Ash, it's not. Because these, you know, as you get to the asymptote right here, you're talking about, I mean, in real physical situations, it will actually reach Qmax. Mostly because, Ash, what we measure is the voltage across the capacitor, right? Just like in this little thing right here, what we would measure would be the voltage across the capacitor. And eventually it's going to reach, see, like it happened right there. Eventually it's going to get to 8.9999 volts, and then it's just going to read 9 volts, because it doesn't know the difference between 8.999 volts and then adding more 9s on, if that makes sense. So it will technically get there. Nathan says, when batteries lose max charge over time, when batteries lose max charge over long-term usage, and accurately measuring its charge becomes harder over time, is this related to this concept? Possibly. There are induction charging freeways being built. I think it's still a concept, but it's a thing. Yeah, that's right. Induction charging is like wireless charging, basically, right? That's how the wireless chargers work. Is through induction, inducing a current. They're doing an induction charging pilot program in Los Angeles. That's cool. Okay, Ty's telling me we should keep the absolute value in the natural log, and Q prime is smaller than CE, and CE is positive. Ah, I see. So we should have not done that thing I did. That thing I did messed us up, basically. Where I factored a negative sign out right here. We should have just left it the other way, and it would have fixed it probably, right? Anyway, it's 9:08. We're well past time at this point. I don't want to keep y'all any further. We'll do some problems with these next time, with these RC circuits. One thing I left off is you can take the derivative of Q here, and it'll give you the current. So the current's going to look like e to the negative t over RC. Okay, I'm stopping the recording right there.